Hi everyone, welcome back to part 2 of this presentation. Thanks for checking back. Okay, so I'm going to talk about, well, one or two of my own ideas. I don't actually remember. Let's see. So the first, okay, so the title of the second part is geometric deformations of singular context structures and future directions. Right, you will see what I mean by this in a second. So let me start by sort of making sort of observation that maybe you've made before, which is that one parameter families of objects in context topology are quite important, right? So if you have a one parameter family of context structures, let's say a smooth one parameter family, then by gray stability, the context structures at the endpoints of the one parameter family are isotopic. So, for all intents and purposes, they're the same. And the same, well, it's also true that one parameter families of Riemannian metrics are quite important in the study of Riemannian geometry. So if you think about, say, a Ricci flow, then what you have is you start out with symmetric, you find a sort of good way of generating one parameter family. And while it's absolutely not true that the initial metric and sort of the end product are related in any strong way, it's certainly important to study well, one parameter families feature heavily in this theory. Yeah, in fact, let me mention that sort of in a certain sense, Riemannian geometry, well, the opposite holds from contact topology. So the space of Riemannian metrics is path connected, right? So any two Riemannian metrics can be connected by one parameter family of Riemannian metrics, and it's sort of no information is preserved. But it doesn't mean that one parameter families are not important. Well, okay. Yes, just accept the statement for now. And now, sort of if you remember what I talked about in the first part of this presentation, then there is the correspondence between Riemannian metrics and potentially singular contact forms. So how does this work? We have a Riemannian metric. Then we can use this Beltrami operator, solve an eigenvalue problem to get a potentially singular contact form. And given a contact form, you can go back to Riemannian metrics by actually to a compatible one, a weakly compatible one, by just picking one of these Riemannian metrics, where G psi is just a sub-Riemannian metric on the plane field defined by the kernel of alpha. Okay, and now we can sort of ask the natural question, can this correspondence be lifted to the one parameter family level? So if you have a one parameter family of Riemannian metrics, does this induce a one parameter family of contact forms, potentially singular contact forms? And conversely, if you have a one parameter family of, say, honest context forms, does this give you a one parameter family of Riemannian metrics? I can tell you right now that the second direction I just talked about now is, I mean, not exactly trivial, but fairly easy. You just need to check smoothness and all of these things. But the other direction is far from trivial. It sort of turns out to be true, at least generically. So the answer is yes, sort of. There's this thing I proved last year, which tells you that if you take a generic smooth one parameter family of Riemannian metrics, then this induces a, if the family you start out with is smooth, it induces a smooth one parameter family of singular context forms, all of which are compatible with the associated Riemannian metric. The proof is, well, depending on your tastes, it may not be exactly fun. It involves sort of a bunch of functional analysis, though. Yeah, so sort of what you need to analyze is whether or not you can avoid double eigenvalues along one parameter family. Well, double eigenvalues of this Beltrami operator along one parameter family of Riemannian metrics. Okay, so that's functional analysis, not exactly topology. And anyways, why should we care about this? Well, at least I think it's quite cool that this procedure of taking one parameter family of Riemannian metrics and getting sort of, an associated one parameter family of weakly compatible contact forms that may or may not be singular. Well, it gives us the option of deforming contact forms or singular contact forms alongside a deformation of the ambient geometry. And I think that's sort of cool. Well, and one of the reasons why I think that's cool, it's not just because, sort of the idea sounds cool, but because of the following sort of idea. So recall that if you have a weakly compatible pair of Riemannian metric and contact form, and they're sort of compatible enough, and G, the metric, has good enough curvature properties, then this implies that the kernel of alpha is tight. But now, suppose that you only know that you have a compatible enough pair, but actually G doesn't have any good curvature properties. Then maybe you want to deform G and make it have better curvature properties. And maybe in this way you can show that even sort of weaker assumptions on the curvature are enough to conclude that this compatible contact form has a tight kernel. Yeah. For example, if alpha and the standard metric S3 are compatible, then this implies that the kernel of alpha is tight. Yeah, now you could sort of ask yourself, well, we know, for example, that Ricci flow takes a metric that has Ricci curvature greater 0 and sort of converges to this standard metric. And if you can sort of pull along a compatible or weakly compatible contact form, then maybe you can show that the kernel of alpha is tight this way because you sort of preserve compatibility, or actually just weak compatibility along the way. Yeah, the only problem is that if you take your contact form and your Riemannian metric, and now you evolve along this one parameter family of Riemannian metrics, it may happen that in your one parameter family of context forms, singularities occur. And this is really sort of, the central issue here. Before I get to that, let me maybe say, if no singularities occur along this one parameter family, so if we have a path of Riemannian metrics that sort of take some initial metric and go to some final metric, and we deform some weakly compatible alpha 0 along this path, and furthermore alpha t non-singular for all t in this interval, then this implies by gray stability that the kernel of alpha 0 is isotopic to the kernel of alpha 1. Okay, so that would be great. And indeed, it sort of gives you a way of potentially using geometric flows to say something about contact forms. So that would be fantastic. The only problem here is that, as I mentioned, it could be that you start out with an honest contact form alpha 0. Now you do this evolution, this one parameter family of contact forms, and then for some time, alpha 0 is going to stay a contact form since the contact condition is open. But at some point, it could be that there's some singularities that evolve. And that's sort of bad news because you can't actually use Gray's theorem in that case. Okay, and now at some point, maybe the singularity is sort of annihilate again, and well, potentially annihilate again. They don't necessarily have to, but in some cases they have to. And then you get some contact form alpha 1. But since you can use gray stability in this case, it could be that the contact structures are not isotopic. And now, here's the big question. How do we know whether or not alpha t becomes singular? If anyone can abstract this from happening, this would be really big news. I mean, you could then use, geometric sort of flow machinery in contact topology. This would be quite powerful. But at the moment, no one knows how to abstract these singularities from forming, and so it's fairly useless at this point. That being said, I still sort of have hopes for this. So, maybe if you understand singular contact forms well enough, maybe you can maybe you can sort of understand which behavior of sort of the ray vector field you have to abstract in order to in order to know that there is not going to be a singularity that appears. Which brings me to the next topic, which is singularities of these contact forms. They're actually quite interesting. So it's not just that I know that, some solutions of this Beltrami eigenvalue problem are singular. I think it's actually sort of, these singular contact forms are worth studying in their own right. So here's a statement that I alluded to before. So for generic G, singular solutions. Oh, actually, I didn't say this at all. Now that I think about it. Yeah. Singular solutions of this eigenvalue problem have non-degenerate zeros. What does this mean? It means, they roughly look like Morse type singularities. So that's good news. Another thing that we know is that for generic choice of Riemannian metric, there's only finitely many zeros. And, using some elementary stuff, you can also say that there's no more 0 and 3 type singularities. And so there's only, Morse 1 and 2 type singularities. And since we know that, closed 3 manifolds have other characteristic 0, these come in pairs. Okay. But now there's something that's quite interesting from the contact topology point of view, which is if you take a small enough sphere around one of these singular points, so we have a singular point, we take a sphere around it, we make sure it's convex with respect to the contact structure, then it's going to be true. And then it's going to be true that this S2 has contains has a neighborhood that is over twisted. So we put it like this: any small S2 enclosing convex S2 enclosing a singularity. Singularity is over twisted. Another way of, the consequence of this is that any neighborhood of a singular point is over twisted. Okay. Now, this is sort of curious, but it also implies something for the dynamics of the associated rate vector fields, at least in certain cases. So we can adapt an argument that Hofer did in his paper, in which he proved the Weinstein conjecture for over-twisted contact manifolds. And the argument is sort of the following: as long as you can find. Okay, so I told you, if you take a sphere that is sort of small enough, that encloses the singularity, then it's going to have an over-twisted neighborhood. But now you can sort of take a shrinking family of spheres. You can bring them into a position that is sort of nice with respect to the ambient context structure. Namely, what I want is for each of these spheres to have just for their characteristic foliations, to just have two singular points, one elliptic positive, one elliptic negative. And now, if you can sort of run a certain pseudo-holomorphic curve argument, basically what you want to do is start pseudo-holomorphic curves at these singular points. And if you can make sure that these pseudo-holomorphic curves don't run into the singularity, then you actually know that there exists a sequence of closed Grabe orbits with. Okay, maybe I should have said this earlier, but these singular context forms, you can think of them as context forms that are defined just in a complement of a punctured free manifold. And so you can, look at their associated rate vector field. And so if the hypotheses that I talked about are satisfied, then actually there exists a sequence of closed Grabe orbits whose length goes to 0. And, there exists at least, sort of a subsequence that converges to one of the singularities of alpha. It sort of just vanishes towards infinity or however you wanna think about this. That's, I think, pretty cool. It's unclear to me how often this actually happens. So there's, singular context forms where I can just force this sort of behavior by constructing some Levi pseudo-convex hypersurfaces in the symblectization of the singular contact manifold. But yeah, I don't feel like I've found a satisfying condition that tells me that the pseudo-holomorphic curves are just not going to, escape into this singular point across R. So if you have sort of interest in the dynamics of rate vector fields, and you feel like maybe the compact case, is done, well, maybe not is done, but maybe you want to do something in a non-compact case, I think this is something that people would care about, even, from a rate dynamics point of view. Then this is a sort of question I think that you could look at. I mean, these singular context forms, they provide you with a non-compact contact manifold in a way, but you kind of understand something about neighborhoods of these singular points. So sort of, it's not just a random contact form on a non-compact free manifold. You understand much more than that. And maybe, you care about this sort of thing, and I would be very happy to see people think about this. Anyways, what's cool is that you have wild dynamics in this particular setting, and I think this is just very cool. You have this shrinking family of Rabe orbits, and it's just very nice. Yeah, in particular, it would be interesting to know whether singular context forms, like their non-singular counterparts, satisfy some sort of Einstein conjecture. And yeah, if you make any progress on this, I think people would care. Yeah, so let me conclude with the following upshot, which is actually very little is known. It's known about metric contact topology. So another, well, a slightly nicer way of putting this is that there is a lot to do. Hopefully I managed to convince you that finding out more about the way in which Riemannian metrics and contact forms interact is sort of interesting for all kinds of reasons. And it would be cool to see more people sort of trying to make progress in this direction. In particular, if you know pseudo-holomorphic curve theory and or ECH, maybe plus some geometry, but you can always learn this. The geometry part is not actually that complicated, I think. You could potentially have a big impact and do something that people care about. If you are interested, come talk to me. Yeah, let's see how much I can tell you, but yeah, there's not too many people that can actually tell you something about this intersection of fields. Yeah, so again, if you care about this, feel free to talk to me. I'm very happy to talk to anyone about this. Yeah, so this concludes my talk. I want to thank you for listening. And yeah, I hope you got something out of this. Yeah, and I'm very happy to talk to anyone about this. So hopefully see you in the office hours. Bye.